Hi everyone, welcome back. My name is Jingyi. I'm a PhD student from Professor Zhang's group at CUHK. In this tutorial, we will walk through a complete end-to-end transition state discovery workflow using CHEMSMART and Gaussian. Starting from an initial TS gas structure, we will cover how to set up a constraint optimization if needed, run the main TS search, verify the reaction pathway using intrinsic reaction coordinates calculations, re-optimize the resulting IRC endpoints, and finally calculate highly accurate single-point energies. By the end of this video, you will understand how these different Gaussian subcommands seamlessly fit together into a production-ready TS workflow. We will also cover how to set up multi-step link jobs. CHEMSMART exposes a rich and flexible set of native Gaussian options. I will briefly display the help output on the screen now, and then we will jump straight into a real-world TS search example to show you how these components interact in practice. In practice, you only need to feed CHEMSMART an input file once at the beginning of the workflow. For all subsequent steps, you can simply pass the output Gaussian log files directly. CHEMSMART is smart enough to automatically extract the final coordinates from them. If your initial TS gas is highly unstable, or if you need to manually guide a specific bond length, it's a good idea to start with a constraint optimization using the MORAD subcommand. This allows you to pre-shape the structure before starting the rigorous TS search. Today, we will look at a simple SN2 reaction. To monitor the bond formation, the MORAD subcommand constrains the distance between atoms 1, 2, and 3. Note that atom indexing in CHEMSMART is 1-based, so ensure it matches your visualization software. This command will write a Gaussian input with a constraint block appended, submit the calculation, and append a MORAD suffix to the output file. You can customize this suffix using -a or replace the label entirely using -l. Here is the completed output file. We can check the vibrational frequencies to verify. If you don't need a constraint setup, you can launch the TS search directly from your original TS gas. Otherwise, simply feed the morad.log file to CHEMSMART, and it will extract the final structure for you. For most projects, this is the main command you will run. If you need to keep a specific part of your molecule rigid during the transition state search, you can freeze selected atoms. For instance, appending -L258 right after the TS subcommand will freeze these specific atoms' indices. Be careful not to confuse this with the global Gaussian level -f flag, which is used to specify input files. If your TS optimization converges, but your frequency calculation yields more than one imaginary frequency, don't panic. CHEMSMART features a quick reaction coordinate subcommand. This tool displaces the structure along a specific vibrational mode to clean up unwanted imaginary modes. Here, -M2 selects a second imaginary mode, -A adjusts the displacement amplitude, and -LTS instructs QRC to automatically trigger a new TS optimization on the modified structure. Once you locate a TS with a single imaginary frequency, you must verify that it actually connects your intended reactant and product. To do this, we run an IRC calculation, which follows the minimum energy pathway downhill from the transition state. While you can fine-tune the IRC tracking directions and stepped parameters later if a calculation stalls, CHEMSMART's default IRC settings are optimized to handle most standard workflows right out of the box. Because IRC endpoints are rarely fully converged minima, the next step is to take those final structures and run standard geometry optimizations. These two quick jobs re-optimize both the forward and reverse IRC endpoints. Once converged, you should visually inspect these structures to verify they match your expected chemical reactants and products. Finally, we compute high-accuracy single-point energy on our optimized structures. This is a standard computational strategy. We perform the expensive geometry optimization at a lower, affordable level of theory, and then evaluate the final electronic energies at a higher level of theory or with advanced implicit solvent correction. These specific functional, basic set, and solvation models are securely managed by your central project settings. A quick but important note on how CHEMSMART handles your calculation by default. In a standard workflow, CHEMSMART uses the settings in the gas section for the geometry optimization, and the settings in the solvent section for the subsequent single-point calculations. Take a look at example 1. Here, these parameters will guide the gas phase optimization, while these parameters will be applied to the solvent single-point run. But what if you want to run everything under a single environment? Let's look at example 2. Here, the gas section is left blank. In this scenario, CHEMSMART automatically uses the settings in the solvent section for both the optimization and the single-point jobs. You can also customize this further, as shown in example 3. You have the flexibility to specify a solvent directly within the gas section. If you do this, CHEMSMART will perform the initial geometry optimization explicitly in that solvent. This flexibility lets you tailor your configuration to match your exact project needs. For a deeper dive into these configuration files, check out our previous tutorial linked here. CHEMSMART also supports complex multi-step workflows, such as preparing broken symmetry inputs via Gaussian link jobs. The supported options are displayed below. For example, this command will optimize an open-shell singlet structure. If you need to apply multiple gas parameters simultaneously, you can separate them with a comma, and CHEMSMART will format the Gaussian root string accordingly. Additionally, for broken symmetry calculations, you can easily override the parent molecule's global setting by specifying the -C flag for charge and -M for multiplicity. To keep this introductory tutorial focused, we are intentionally skipping a few advanced options. While powerful, those features are best saved for dedicated deep dive videos. For your first TS workflow, it's much cleaner to treat each calculation as a single, well-defined step. To summarize, CHEMSMART standardized this often tedious Gaussian TS workflow. It takes care of generating consistent input files, organizing automatic HPC job submissions, and ensuring your calculation sequences are easily reproducible for publication. In this video, we went from a raw TS gas, refined it using MORAD, located the true transition state, mapped the reaction pathway via IRC, optimized the chemical endpoints, and computed final single-point energies. You now have a complete, robust, and reproducible transition state discovery workflow at your disposal.